welcome back, students. So now we will go into the mechanisms, the couple of mechanisms that are there for the creep, and we will understand their formulation. Okay, so like we said in the previous lecture number 26, that there are primarily two types of mechanisms: diffusional creep and dislocation creep. Where in the diffusional creep, only diffusion and no other components like dislocations are actually contributing to the creep. While in dislocation creep, if it is climb control, then diffusion, particularly of the vacancies, and the dislocation together contribute to the dislocation creep. And in the case of glide control, only the dislocations contribute to the creep. And apart from this, we have mentioned it earlier, there is grain boundary sliding, which can be looked at as an aid to the other two mechanisms. It cannot occur on its own, and its primary role is to heal the defects that may have caused because of the movement of the grains. And this is also something we looked at. What is the range of stresses and temperature in which they work? So this diffusional creep, if you go towards the top side, it has more temperature dependence, and if you go towards the bottom side, it has more stress dependence. Okay, so now coming to the diffusional creep, and like we said, this is applicable at higher temperature and low stresses. So now let's say you have a material where these hexagonal thing that you're looking at are grains. And if you apply a stress at high temperature with low stress, not much, then eventually what will happen is that the grains would become elongated and the final shape would be like this. It is an exaggerated image, but it shows the overall transformation that will take place in the dimensions of the component. So it was like shaped like this, and it will become elongated, including the grains inside it. And if you had drawn a circle, it would have become ellipse. So grains elongate, is it without the involvement of dislocations? And if it is a climb controlled process, then yes, it is without the dislocations. So what is happening over here when you are applying stress? Then vacancies are getting generated over here, and the concentration of vacancies exists from here to over here to here. And similarly, you are applying stress here, so there are a lot of vacancies over here. So vacancies concentration, higher concentration and lower over here, higher over here, lower over here. And because of this concentration, vacancies move over here. And when the vacancies move like this, the atoms would move in the opposite direction. So the atoms would move like this. And eventually you would have dimensional change like this. So after the end of the flux, so dotted line is before the flux and the dark line is after the flux. So you can see this is the movement of vacancies and this is the movement of atoms. And eventually the component would get a shape like this. And yes, it is happening all without the involvement of dislocations. So what is happening? Like we said, excess vacancy is generated in the tensile region, and this is the vacancy equation, the concentration equation. So since there is a vacancy concentration gradient, higher here, lower over here, so vacancies start moving in this direction, and the atoms move in the opposite direction, leading to the change in the dimensions. So vacancies move in response to the applied stress, as we saw earlier. Now this movement of vacancies can occur in two ways: through the lattice or through the grain boundaries. So for example, if you are looking at one grain, so here the vacancies could move inside through the grains, or vacancies could have moved along the grain boundaries. When they are moving through the lattice, then it is called Nabarro-Herring creep. When the vacancies are moving through the grain boundaries, then it is called Koebel creep. And there is a particular temperature regime where each of them would be active. And that is why they have separate names for this. And we also mentioned vacancies move opposite to applied stress, atoms move towards loading direction, leading to extension. So if you're looking at grains, and so here, this is the direction of movement of atoms, this is the direction of movement of vacancy. So vacancy, this is a vacancy source, and the vacancy would move. Sorry, the vacancies are, this is the source and this is the sink. So in a shape like this, where the stresses are being applied like this is the vacancy source, vacancy would move. Here it is being generated, and here somewhere over here, they would get absorbed. And in the process, you would see that the shape of this grain would change to something like this. And this is happening, as you can see, through the grains. Inside the grain, vacancies are moving. On the other hand, the vacancies could have been moving along the grain boundaries. So the vacancies would have moved from over here to over here, from over here to over here. And in that case, you would see, you would call it Koval creep. And overall, the grain size would also change over here. So you can see this is the original line, this is the new line, this is the reference line. And since the grains have elongated, so this is, these reference lines have moved in, and the corresponding lines remain beyond, and they basically shift with respect to each other. So both of them mechanism can lead to the change in the dimension and thus the creep, and it is the temperature which will decide which one will dominate. So this one, Navarro-Herring, which is the diffusion through the lattice, we know that lattice diffusivity is higher at higher temperatures. So this one is dominant at higher temperatures, while grain boundary diffusion, which is dominant at moderately lower temperatures, this is the Koval creep you would see would be dominant at those lower, moderately lower temperatures. So in response to the applied stress, vacancies preferentially move from surfaces, interfaces of the specimen transverse to the stress axis to the surfaces, interfaces parallel to the stress axis, thus causing elongation. Diffusion of vacancies in one direction can be thought of as flow of matter in the opposite direction. We saw that the vacancies were moving in one direction and the matter was moving in the other direction. The diffusion could occur predominantly via lattice at high temperatures or via grain boundaries at lower temperatures. When it is via lattice, it is called Navarro-Herring, and when it is via grain boundaries, it is called Koval creep. This process, like dislocation creep, which we have not yet discussed, which the dislocation creep where it involves climb, is controlled by diffusion of vacancies. So we are already giving you a hint that dislocation creep involving climb is also controlled by diffusion of vacancies. And this one is also something we saw is controlled by diffusion of vacancies. But diffusional creep does not require dislocations to operate. Okay, so we found that no dislocations are required, even though deformation strain is taking place and mass transfer is taking place, but no involvement of dislocations is taking place. So diffusional creep can be either Navarro-Herring creep or Koval creep. Navarro-Herring creep at high temperature through the, where the diffusion is taking place through the lattice. Lower temperature, Koval creep, and the diffusion is taking place through the grain boundaries. And here is the equation which defines them. So Navarro-Herring creep, high temperature, T is approximately Tm. So here the range is also mentioned, very close to the melting temperature, and slightly coarser grain materials. Vacancy diffusion through lattice, and the strain rate would be given by this equation. So here P is equal to 2 and N is equal to 1, and D is replaced by DL to represent lattice diffusion coefficient. Koval creep, relatively lower temperature, not low, mind you, it's relatively low. So T is still of the order of 0.7 Tm. And you would also see it is more dominant when the fine grains are, the material has fine grains, and vacancy diffusion through grain boundaries. So here the diffusion, mode of diffusion is through the grain boundaries. And this is the equation. So here P is equal to 3, N is equal to 1. And this is the form of the equation that you would obtain. And actually, again, this is something it should have been C. So let me. Okay, so now I have corrected it. This is epsilon dot NH. For Navarro-Waring, there is epsilon dot C for Cobble creep. And here P is equal to 3, P is equal to 2. This is 2, N is equal to 1. This is N equal to 1. Here P is equal to 3 and N is equal to 1. So that was about diffusional creep. Now let's move on to dislocation dependent mechanisms. Now dislocation dependent mechanism, we can separate it primarily again into two parts. One where creep, cross-slip or glide is the mode of plastic deformation. The other where the climb is the mode of plastic deformation. So dislocation climb. Now this dislocation climb is the one which is more sensitive to temperature and hence more dependent on temperature, and more, you can say that this particular creep phenomena is more temperature sensitive. Here edge dislocations, when they are piled up against an obstacle, because of the climb motion, they can climb to another slip plane and cause plastic deformation. It is to be noted that at low temperatures, these dislocations are sessile and become glissile only at high temperatures. So you can see that this particular dislocation movement, this is not present there when the temperatures are low. This is present only, this gets activated only at higher temperatures. At lower temperature, these are sessile, meaning they cannot move. And only when the temperature is high, then the vacancies come into picture, and then the vacancies lead to the climb of these dislocation, and the dislocations can start moving. So the climb process itself is activated only at higher temperature. Rate controlling step in this particular process is the diffusion of vacancies. So the same equation, D equal to D naught exp minus Q by KT. Higher the stress applied, more number of dislocations get unpinned from the precipitates and barriers per unit time, and hence higher creep rate. So even though this is temperature dependent, meaning that this gets activated only at high temperature, but still it is still sensitive to the stresses, because higher the stress, higher the number of dislocations that get unpinned, and hence more and more creep will take place. So strain rate gets increased because of increasing stresses. And this, you can see this effect that this is dependent on the stress, because N is equal to 3 to 8. So the order of N has become higher. Earlier, for the diffusional creep, we saw N was of the order of N equal to 1. And D over here is mostly dislocation core or lattice diffusion coefficient. So this is the general equation, and at constant grain size and temperature, we know that we obtain an equation like this, which is called power law, which is a climb controlled creep. So you can see it is very dependent on the stress, assuming that the temperature is constant. And so strain rate is equal to P prime times sigma to the power N, where N is of the order of 3 to 8. Now, if you plot it on a log-log plot, then it will be a straight line. So where on the y-axis you have log strain rate, and then on the x-axis you have log sigma. It will come out to be a straight line, and the slope would be equal to N. So from the slope, you can find out what is the value of N. And this kind of behavior exemplifies that it is a climb controlled creep process. However, you may also experience a behavior like this, where you would see that the power law breaks down. So there are two different values of N, and this happens when when N exceeds 8. So in those cases, you may see something like this. And when we say climb controlled creep, you must also realize that climb will almost always be followed by glide, because climb is only allowing the dislocation to jump over the dislocation, some barrier. It may be a grain boundary, it may be a precipitate, it may be some other obstacle. But in the end, the dislocations have to move. And when they will be able to move mostly by glide mechanism. So creep rate is controlled by how rapidly the dislocations can overcome obstacles that obstruct their motion. So what is the role of glide control? What is the role of temperature in the glide? So some of these glide will be thermally activated dislocation glide. Usually glide is not thermally activated process. It can ensure much, you can say, higher kinetics for the glide and lower resistance to the motion of the dislocation. And glide, when this glide is also participating, that may also lead to power law breakdown, as we saw earlier. So glide is also contributing to that power law breakdown. Now about the mechanism for power law creep or the dislocation creep, which is primarily climb controlled. So let's say we have a dislocation which gets piled up. It can be because there is a lock, something like a quadrilateral lock, or maybe because there is an obstacle like this, a precipitate. Then what climb does is that it allows the dislocation with because of the presence of vacancies to leave the plane. And once they leave the plane, they can go over, and then whenever the glide forces get reduced, they can start gliding and thus enable the crossing over of the dislocations. So dislocation glide aided by diffusion, that is climb. Glide results in almost all strains, but climb controls the velocity. So as you can see, if you look at the strain, then the strain is mostly because of the glide. But the rate controlling step is still the climb step. And therefore, it is given by this, where D is the dislocation core or lattice diffusion coefficient. So the vacancies are moving either through the dislocation core or through the lattice, and it is their diffusion coefficient which will control the strain rate. And here again, as we said earlier, N is of the order of 3 to 8. So how does the dislocation climb over the obstacle? So here is a schematic. So let's say these dotted lines you see are the slip planes, and here is one dislocation. So dislocation is gliding, 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 and it reaches over here. Now, the shear stress that was moving this dislocation is not able to move the dislocation in further because there is more resistance from this obstacle, which may be a precipitate or a lock. So even a lock like a lower quadrilateral lock can cause the dislocation to stop movement. And therefore the glide force that was acting on it is not able to move it any further. However, if the temperature is high, then with the aid of the vacancies, this dislocation can climb to another glide plane. And from there again, on a particular glide plane where the glide force is sufficient to start moving it, it can move. And so here is the final position, and there should have been a green line. So this way, the dislocation is able to climb. But what is the role of vacancies here? Now we know that if there is a dislocation, there is a compressive stress here, and there are tensile stresses over here. And if there are vacancies, so these vacancies are shown in square boxes over here. So if there are vacancies over here, they will tend to move to the core of the dislocation. They will have a tendency. And at higher temperature, the equilibrium vacancy concentration is high. We know that. And therefore, there is a lot more probability of the vacancies being around, and therefore they will have higher probability to diffuse to the bottom or the core of the dislocation. So after some time, some of these dislocations would have moved over here. And what this does is cause the climb of the dislocation. So this is the de facto climb of the dislocation. Here, the dislocation was here, and here now it has jumped all the way up to here. And similarly, so after some more steps of jumping or climbing, the dislocation may reach here, and then the climb force may be sufficient to push it over here, and then it can move freely. So you can see that the rate controlling step is the climb of the dislocation, and thereafter the dislocations glide. So overall creep formulation can be given like this. The Navarro-Herring creep is of the order of 7 to 15, P is 2, N is 1. Cobble creep, these two are diffusional creep. So A is 30 to 50, P is 3, N is 1. Power law creep, A can be very, very high, and P, which is this one, is of usually 0, or basically it is not dependent on the grains, or sometimes we say that we are taking a very large grain sized material where grain size, it becomes independent of grain, and N is of the order of 3 to 8. Now coming to the third mechanism. Now I'm putting it in quotes because, as I said earlier also, this is not an independent mechanism of creep. This is just a supporting mechanism. So here grains in a polycrystalline materials move relative to each other. So earlier we were seeing the elongation of the grain, but now we are talking about the movement of the grain or sliding along the grain boundary. So grain boundary sliding is necessary for the prevention of void formation in the material. So let's say 4 grains are depicted here and you draw a line over here. Now because of the diffusional creep, these grains would become elongated. Now when they become elongated, so their final structure may look like this, because it is not exactly what will happen. So if once a void is formed, then the material is doomed to fail. So along with this diffusional creep, these grains would keep shifting, and they will keep shifting all the way until there is no void there. So kind of healing of void takes place due to grain boundary sliding. And that's why I mentioned earlier that this is not an independent process, but something that occurs concurrent with the other process, primarily the diffusional creep process, in order to heal or avoid the formation of voids. So mind you that even the formation of voids would not be so easy. It will need a lot of very high stress. And therefore, this is a mechanism which is, you can say, low energy path. So because the grains are becoming thinner, so they will tend to slide. The grain boundaries would tend to slide the grains so that no void gets formed. So diffusional flow and grain boundary sliding can be considered sequential process. Mass is first transferred by noble herring or cobble creep. Grain shape changes to thinner and narrower grains, followed by grain boundary sliding. So it is a very incremental process. You would not literally see a void formation until the process becomes extreme, where the temperature and probably the stresses are too high, because of which the movement in the first step becomes too large. Movement of the grains become too large in the first step, so that it is not able to, the second process, which is the grain boundary sliding, is not able to keep up with it. And in that case, you may start to see the voids, which is shown here in one of the micrographs. Now there is another mechanism which is called as grain switching mechanism. So here basically what is happening is that the grain shape is preserved by grain switching mechanism, but it produces a strain, and eventually the overall, you can say, the shape of the component changes. So let's say these are the 4 grains, and then the mass is moving like this over here, and therefore eventually there will be a crossover shape, something like this, and eventually because the mass keeps moving in that direction, therefore eventually this grain would form. So overall the grain shape is preserved, but because of the switching, the strain has taken place and overall dimension has changed. So this is another mechanism by which dimensions inside the component can change. Coming to still another mechanism inside the dislocation mechanism, and it is called Harper-Dorn creep. So Harper and Dorn in 1957, they were studying aluminum at high temperatures at relatively low stresses using very large grain size. So initially it was expected that it will be a diffusional creep mechanism because temperatures are high and stresses are low, and the creep rate, which would also mean that the creep rate should be controlled by grain size. So if you change the grain size, the creep rate would change. However, what Harper and Dorn observed was something different. They found that steady state creep increased linearly with applied stress. Activation energy for this creep rate was that of self-diffusion. Okay, it was not that of the Nabarro herring or Koval creep. And the creep rate was 1400 times greater than the theoretical rates that would have been calculated using Nabarro herring or Koval creep. So this clearly means that this is not NH or Koval creep type of diffusional creep mechanism. Creep under, moreover, what they found was that creep under these conditions was independent of grain size. So this was certainly not a diffusional creep. So what they finally concluded was that it was a low stress creep at high temperature, where when materials have very large grain size, then they can occur by dislocation climb mechanism. So even for very large grain size, dislocation climb mechanism can start to operate. And in that case, you can have strain rate something like this. So here sigma by G is equal to 1 and not 3 as it was for other dislocation mechanisms. So comparing Nabarro herring creep and Koval creep, which are diffusional creeps, with the HD creep. So these are the equation. So this is your strain rate for Nabarro herring, this is strain rate for Koval creep, and this is strain rate for HD. And what you see here is that this one is independent of D, which is small d, grain size, which means it is grain size independent. And what you also see is that it is different from the power law creep in that it is sigma by G is not of the order of 3, which is what we have observed earlier. So N is still 1, like in the Nabarro herring and Koval creep, but it is independent of grain size. So overall, if we want to put a summary of how the equations change with different mechanisms and models, then this is a very good slide as a summary. So this is the Mukherjee-Bird-Dorn equation, which we can consider as the most general equation, where if you take constant grain size, then this is the equation that we derive, and at constant temperature it becomes the power law, and at constant stress you can put as equation like this. And if you put the diffusional mechanism, then the strain rate can be given by the Nabarro herring or the Koval creep, where form of the equation is same, only the D is changed. No, actually there is one more change, which P is equal to 2 here and P is equal to 3 here. And D is here DL for the lattice diffusion coefficient, and D is DGV for the grain boundary coefficient. And here for the power law, usually you will have N equal to 3, 3 to 8 actually. And if you go for the Harper-Dorn equation, which we saw is true for very large grain sized materials at low stresses and high temperature, then we get an equation like this. So here it is independent of the grain size, but is still proportional to the sigma by G to the power 1. So this summarizes all the various possible equations that are there that we have gone through in this lecture. So it also describes the different mechanisms there. So those were the independent mechanisms, but of course we can also have multiple mechanisms when more than one creep mechanism may be operating. And there are two possibilities. Sometimes the mechanisms may be operating independently. So overall creep rate is the sum of the creep rate due to each mechanism. The result is like two mechanisms acting in series. The overall strain rate depends primarily on the most rapid mechanism. Or the other possibility is where the two mechanisms may be required to operate simultaneously. So for example, grain boundary sliding requiring another mechanism like novel herring or Koval creep. Climb controlled creep requires climb before glide. So these are the mechanisms, these are the methods where two mechanisms operate simultaneously. The overall rate is determined by the potentially slower mechanism. So this one is basically one after the other, and therefore which one is slower, would be the one which will control the rate. While here it is the sum of these. So if one is very large, then that would be the one that will control the overall rate. So we can have multiple mechanisms also, and that too, it can happen in two ways, either independently or simultaneously. Now, coming to one of the most important aspects regarding creep, we have been saying that there is a particular regime of stress and particular regime of temperature where different mechanisms are active. This is the slide which summarizes those in a schematic way. On the x-axis, we have normalized temperature or homologous temperature. On the y-axis, we have normalized stress. So this is the applied stress and G is the shear modulus. And over here, you can see low stresses and high temperature. We have Navarro-Herring or the lattice diffusion creep that is dominating. And this is even lower temperature and low stresses where Koval creep or the grain boundary diffusion is dominating. Now, when we go to higher stresses, then we know that dislocation creep gets activated, and there is also two separate regimes, high temperature regime and low temperature regime. And if we increase the stresses very high, then it is the dislocation glide, which is actually dominating. And this is the theoretical strength of the material. So beyond that, the material cannot sustain this kind of stresses. So ideal shear strength, plastic flow of the material can take place without dislocations by simple glide of one atomic plane over another. And this is something that will not happen normally, because before that you would have already deformed the material using plastic deformation. Dislocation glide. This involves dislocation moving along slip planes and overcoming barriers by thermal activation, for example, in cross slip. So this is mostly guided by glide or cross slip. Then we have dislocation creep, which includes dislocation movement controlled by diffusion of vacancies and interstitials. So this dislocation creep, which is climb controlled, this involves dislocation as well as the diffusion of vacancies. And if we go to the lower stresses, then we have the diffusional creep, which can be Navarro-Herring creep for high temperatures and Koval creep for lower temperature. So Navarro-Herring where the lattice diffusion is dominating, and Koval creep where grain boundary diffusion is dominating. So you can see this is the rough estimate that we gave, and everything falls according to this. And when you are at the boundary, two mechanisms can actually operate, and these boundaries are not very sharp. They are kind of diffused boundaries, so you can have more than one mechanism operating for a good range of stress and temperature. And this is a map that for a real material, in particular nickel, for a nickel material where the grain size is 32 micron. So the grain size has been kept constant, and this is the elastic regime, meaning no deformation will take place. Here Koval creep will take place. Here no Navarro-Herring creep will take place. This is dislocation creep, and this is dislocation glide creep. This is the theoretical strength. So that you can say is the gist of our understanding of creep. Now that we have understood the creep, let's conclude with how do we select a material if it is to be used for high temperature application. So some of the things that we can predict or we can list out based on our understanding of materials and also our understanding of the creep that we have discussed are as follows. High melting point. So what we need is high melting alloys usually has high creep resistance. Metals with high stocking fault energy, because this is metals with high stacking fault energy will has easy slip compared to twinning, and therefore When you have easy slip, then you can have creep. So it is better to avoid metals with high stacking fault energy. Materials should have large grain size, as we saw that diffusion distances are long and grain boundaries do not help diffusion much. And also the size, the overall size of the length of the grain boundaries would be smaller, which contributes a lot to the creep phenomena. Fine precipitates or dispersed solids having high thermal stability are necessary for creep resistance. So when you have high precipitates, fine precipitates in the material, then they prevent, basically they cause dislocation hindrance, they cause hindrance to the grain growth, and also cause hindrance to grain boundary sliding. And each of these would mean a better creep resistant material. So what we want is a material which can have fine precipitates or dispersed solids, and which should be thermally stable, meaning it should not get solutionized at high temperatures. So these are some of the important aspects that we should look at while we are selecting a high temperature alloy. So with that, we come to an end of this section, and also for the overall course, which is mechanical behavior of materials part 2. So I hope you guys like this course, and I would again recommend you that you go back and look at the first part in combination with the second part. That will give you the comprehensive understanding of mechanical behavior of materials. And wish you best of luck for the certification exam. And I urge you all to take the certification exam. Thank you.